Good afternoon. Thank you very much to Angie and TJ and Stan and all of the other people who have helped organize this wonderful conference and keep things going IBL through the year. Also to Norma and Judy and Banning, who take care of lots of the technical things and make everything comfortable and work on time. And also to Mr. Lucas, wherever he is, for his generous long-term support of inquiry-based learning and also of this project. It's an honor to be here and to welcome you with the plenary address, Inquiry-Based Learning to Engage and Empower the Disfranchised. We are excited. Are you excited? Yes. Excellent.
All right. So we'd like to start with some group work. So what we'd like you to do is turn your chairs towards your table so you can actually talk to your table mates and work with them. And what we'd like you to do is imagine that you are a liberal arts or humanities major, and this is the very first day of your required mathematics class. And so share with the other people at your table, what might this feel like to you as a student? And what kind of energy would you as a student have in coming into such a course? So go ahead, start talking.
A few comments, if I could have your attention back. It was very nice to see everybody introducing themselves. That's something that our students don't often do. I had little pieces of hearing many different interesting things, but I will say this. The mood here was much more jovial than it normally is in a class like this on the first day, so you weren't acting very well in that sense.
And normally what we would do when we were teaching a class is we, of course, would ask the groups to share out some of their discussions. But you're a very large group, and we do only have 45 minutes, so unfortunately, when we have these group discussions today, we're not going to ask you to share out. So here's another question we would like you to think about. Now, we want you to change hats and think back, now think as a teacher. Do you have discussions with your students about their mathematical experiences and their feelings about mathematics? And if you do, how does that take place? Okay? So again, talk to each other. Okay.
So to reiterate what TJ and Angie said at the beginning, isn't it wonderful how many people you have to share experiences with here? That's one of the great parts of this conference. Keep doing that throughout.
So when we work with our students, we do spend a fair amount of time having conversations with our students about their experiences and their feelings. And this starts right from the very beginning. So I'm going to show you some quotes from their very first assignment, a mathematical biography. And I'm only going to show you 3 quotes, but these are typical of what we received from the hundreds of biographies that we do each year, okay, over a full academic year. So one student wrote, "Let me just start with the fact that I've attempted college at least 3 times. I swear every failed attempt is due to mathematics." Another student, "As it stands, I'm terrified of this class." And a third student, "For me personally, doing math is immediately associated with struggle and hardship. Feels no matter how hard I try, I am unable to firmly grasp math as a whole or as its individual formulas. Math has always felt like a weight I am unable to lift."
These are the students that are disfranchised, of which we named our talk about. And there are enormous numbers of them, not just in our math class, but in our society in general. To get a sense of the scale of this issue, might I ask esteemed audience, how many math majors do you think graduate from American universities every year?
And you can just shout these out.
Any idea? 1,500, more than 10, less than 30 million are the ones I heard up front. Out of 1.7 million bachelor's degrees awarded in 2010, there were 19,240 bachelor's degrees awarded in mathematics. In 1 year, 19,240. Here's the next question. How many students in 2- and 4-year institutions take a Math for Liberal Arts course every semester? More or less than the number of math majors? Enormously more. 232,000. 232,000. And if you look at these numbers from the CBMS report, if you think about the students who are in general education courses, taking them only for core requirements, so if we add up categories 1, 2, part of 4, and number 5, what do you get? You get over 2 million students. For every math major that we graduate at the end of the year, every fall and every spring, 100 students go through our general education courses, most of them feeling like they've already been disfranchised from this subject of ours. At the 2009 Joint Mathematics meetings, there was an AMS-MAA special session on inquiry-based learning. After the morning session, Mr. Lucas got up and thanked the esteemed audience for their presentations and their questions and concern. But he said he'd heard much about the Moore method for elite students and wondered whether the Moore method works for other audiences, if it can empower the underachiever, the disadvantaged, what we're calling today the disfranchised. Okay? Our answer to that through our project, Discovering the Art of Mathematics, which has been ongoing for 7 years with support from Mr. Lucas and the National Science Foundation, is a resounding yes. This is initial data from our project. We have much more substantial data that is still being analyzed and compared, and we're working some things out. Hopefully by this point next year, we'll have much greater data to share with you, but this is almost 1,000 students, and the question is there something in mathematics that you think is beautiful that you could describe? The light blue is what they said before the course began. The dark blue is what they said after the course began. These are the students who did not want to be there, who hate mathematics, who tell you they can't balance their checkbook. Did you enjoy this course? Look at the enormous shift from people saying that they wouldn't enjoy the course to people who actually admitted that they liked mathematics. Imagine that. Do you think you will remember this class 10 years from now? i.e., when you're a parent and a voter and a citizen and someone on a school board making decisions about budgets. Again, an enormous shift.
So these students are the ones that we want to focus on. And so we'd like to share with you a quote which is very meaningful to us from A Mathematician's Lament by Paul Lockhart. If you haven't read this yet, you really should. Lockhart writes, "Mathematics is the art of explanation. If you deny students the opportunity to engage in this activity, to pose their own problems, to make their own conjectures and discoveries, to be wrong, to be creatively frustrated, to have an inspiration, and to cobble together their own explanations and proofs, you deny them mathematics itself." So no, I'm not complaining about the presence of facts and formulas in our mathematics classes. I'm complaining about the lack of mathematics in our mathematics classes. So many of you, of course, here have taught IBL, and you probably taught them for a lot with our major, so you know how to bring the mathematics into the mathematics classroom. But what we'd like you to do is think about it for the general education students, our disenfranchised. So again, at your tables, talk to each other. How many of you have actually taught a general education course, which we're very broadly defining, by the way? And if you've taught a general education course, have you used IBL? If so, how did it go? If you didn't, why not? Okay, so Go ahead, talk amongst yourselves.
I just wanted to say
Okay. We've hoped you started some good discussions here. Okay.
And we would again like to add that, of course, we're trying to model inquiry-based learning because we want to have lots of people involved. We want you to be the active ones, not necessarily us. But of course, in a huge venue like this, we can't do the kinds of sharing out and talking amongst groups that we would like to do. But that, of course, is something that happens in our classes. What we'd like to do now is we would like to show you some videos and some student work from our actual classes. These are Discovering the Art of Mathematics classes. These are Math for Liberal Arts students who are just taking the course is a general education requirement. Our classes generally have 35 students in them. The mathematical question at hand for the next 10 minutes is the following. For integers a and b greater than 0, what are all possible outputs of the equation 3a plus 5b? Okay. Having said that to a group of mathematicians, you cannot work on this problem right now. That is not the task. The task is to watch the students working on this problem, because I know that you can do this. We want to see what the students did. So put your pencils down. But do take notes if there are things that you see the students doing.
It could be anything. Like, you realistically could get any number.
Except for 0?
Except for 0. You can get any number except for 0.
so prove it gets 71.
What?
Prove it gets 71.
Alright. Well,
Not as easy as
3a plus 5b equals 71.
that's exactly what she's gonna say though.
alright, yeah, well, okay, so all we have to do is bring... Fuck, I hate this.
And it has to be a whole number, so it's not true what we're saying. It can't be like, it's not any.
Yeah, but why can't we get the...
I think we could get 71.
I mean...
Put our minds to it. But it can't be decimal.
No.
Yeah, that's the problem.
Yeah, no, you could, because 21 and 50, if you had 7 and 10. If A is 7 and B is 10, 3 times 7 is 21 plus 50 equals 71.
94. Let me write that down.
94?
Yeah.
324. So if A equals 8 and B equals 70 divided by 5.
Oh my god, 14.
14? Yeah, so if A is 8 and B is 14.
So does it really work for everything?
Because it has to be whole number. We're just using whole numbers. Whole numbers will always get whole numbers. And it's addition, so it's not like we're subtracting.
Yeah, 68, you could do, well, 3 goes into 48 16 times, so if A is 16, 68 minus 48, B is 4.
Good mathing.
So you could literally do it for any number. It's gonna work, as long as you can find a multiple of 3 that will leave, like, a certain number left over. Like, you know what I mean? So like if you had 64 and you wanted to get that, you just take out like 24, so you'd have 24 and 40.
So basically, if we were to do steps, we would like pick a number, pick a positive whole number, and then like we could like we could
Okay. So, now we'd like you to, again, turn to your group mates and discuss the following questions. What did you observe? Were there things that you think were empowering to the students? And where was the teacher? So, go ahead.
And as a reminder, the question was 3a plus 5b equals what? What are the outputs of that equation? Where a and b are positive. No, none, yes.
Okay, so again, we've started some really good conversations. We hope that you can continue these. One thing I did want to think about was the third question. Just a quick show of hands. How many of you thought the teacher was behind the video camera? Wow, less than I thought. It wasn't. It was a student intern, by the way. The professor was off with one of the other groups. This was something that this group did entirely on their own and came up with.
And in general, because there's 35 students and 4 students in a group, we have 8 or 9 groups like this working at a time. So the majority of the class time looks from the student's point of view exactly like that.
Yeah. And this was taping that was done last fall. We have over 200 hours of classroom video that we are working through and looking for and trying. We've posted some of that on our webpage. Hope to get others up to illustrate what goes on in our classroom. All right, so now that is this you? No.
Yeah, so now what we're going to see is we're going to see something that happens after that. That was kind of the discovery phase, right? And then there is generally some kind of sharing. And so we're going to see some sharing from that exact same group.
Proof. We came up with that you can get any number. And basically we figured this out by, well, we made like a list of constraints that we came up with, and you can get any number that's higher than 0. And what you do is you take the number. So we took this number at one point. And what you do is you take the number and you find the smallest multiple of 3 that when subtracted from the number is going to give you a whole number that ends in a 0. So for this one, we did 9. So 3 times 3 equals 9, so A equals 3. And subtracted it, so it was. And then all you have to do is divide that number by 5, and you're going to get B. So B equals. And that'll work with any number that you can really realistically take.
Can someone repeat her strategy?
So you have to get it to a number that has to be 0, right?
Yeah.
By subtracting it by
The lowest multiple is to read it.
Some multiple of 3.
Read it to 0.
Uh-huh.
So what happens if what happens if your number that you're starting with ends in like 5 or something? How do you
Then, so like last night you could take away 45 A's. 15.
Oh, okay. So it's not just
And then you're left
it's not
with-
just the one digit that you can subtract from, it's the whole number.
Yeah.
But you're totally right that what I
Okay, so there was some sharing. And you can also see, by the way, right next to it, there's another solution that another group did, or way they thought about it. So again, in your groups, what did you observe? How does the mathematical argument in the student's presentation compare with their original discussion that you saw? And 3, what role did the student comments play in the discussion, in the presentation that just took place? You know, and the student comments being from the audience, the rest of the class. So, again, talk amongst yourselves.
If we could come back together for a minute. It's hard for me to hear with this many tables, but the tables I am going by, I'm hearing wonderful conversations about exactly the kinds of things that we thought that you might talk about in observing these things. That's what you want to set up in your classroom as well. Okay, so what happens now? What happens now is after there's some sharing and discussion among groups, it's important that there's synthesis into final results. So we wanted to show you some of that synthesis too. This is actual written student work. I know it will be a little bit hard for you to read, but I will help you through some of this. Conjecture. Nice, a conjecture, cool. When a and b are integers greater than or equal to 0 in the expression 3a plus 5b, then you can get all positive integer values with the exception of 1, 2, 4, and 7. Excellent. So after, in the first paragraph, it concludes by saying, so you can see that none of them come out with the answers 1, 2, 4, or 7. After that, after you get to the value of 9, you can get from 10 to 19, and you can use these numbers to get every single other positive number. Once you get from 10 to 19, as you can see we did in our chart above, you will be able to continuously add 10, which is 5 times 2, to get the next set of 10 numbers after 19, and so on and so on and so on. Beautiful argument. The next one also begins with a conjecture. And then they say, they have these things listed out. They've made sense of some pattern in there. They have them listed, how you get 3, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, and they've highlighted this middle part. And in this middle part, they say, for the first entry, which is 10, add 10 and subtract 9. Subtracting 3 3s and then adding 2 5s. Think about that. If you add 10 and subtract 9, you've added 1 to get to 11. And then it says, add 6 and subtract 5, subtracting 1 5 and then adding 2 3s. Add 6 and subtract 5 again. Add 10 and subtract 9. Then add 6 and subtract 5. Do you guys know the finger trick by counting by 9s? Right? We had done that, and this group decided that they would figure out a way to do it like that. They're trading in 3s for 5s as if they're making change, as you would change in 10s for 1s on this finger trick. Brilliant. Okay? Another one. Very much the same idea, except for they've written it and they say, from here you can use 3a plus 5b to increase the solution by 1 using the following algorithm. These aren't math or computer science students. Awesome. Increase a by 2. In other words, add 2 3s. Decrease b by 1. Subtract 1 5. Decrease a by 3. Subtract 3 3s. Increase b by 2. Add 2 5s. Increase a by 2. Decrease b by 1. Repeat. That's their proof. Awesome. Last group. Last group starts off showing that you cannot get the certain values, the 1, 2, 4, and 7. And then they start making this chart. And the chart is kind of tough to read, but the one on the far left starts with 18, 21, 24, 27, 30, 33, 36, and so on and so on and so on. Everything that's congruent to 0 mod 3. The next chart is everything that's congruent to 1 mod 3. Of course, they didn't say that, but they found a pattern, and they have this nice diagonal that runs through this whole thing, showing you why you can get every single one of them. That, of course, was the idea I had in my head about how you would solve this problem. And I could have walked into the class and lectured about that in 10 minutes, and not a single student would have had any epiphany about that whatsoever, and I'd never seen these other beautiful proofs that these students did. But instead, I kept my mouth shut. Got all these neat proofs.
So before we ask you to think about that, I just want to answer one question that was asked over here. Somebody said, is this still the first day of class? And no, it's not. But if you looked carefully at the students' clothing, you could probably, this was a fall semester. This was very early in the fall semester, within the first couple of weeks that they were doing this. So this is not deep into the course. All right? So here's what we'd like you to talk about in your groups. Where or how do you think IBL played a central role in the students' investigation of this problem? Okay?
Just as kind of a 2-minute wrap-up.
All right.
So we showed you one problem. Here's the million-dollar question. How do you make a whole course like this, right? How do you create environments where this type of inquiry happens in general education? Students' mathematical skills, interest levels, and attitudes and perceptions about mathematics are so challenging, you got to string this together for an entire course. How do you do that? Okay, well, our expertise is in math for liberal arts, and our project is Discovering the Art of Mathematics. We have copies of all 11 of our books that are out there. We also have lots of copies of our brochure if you want to grab one of them. All of the books are freely available online for free downloads. You can send them to your copy center, have them copied, they are good to go. What do they look like? There's one, and you open it up and you see what? Chapter 2, the existence of the square root of -1, a case study, and what it means for something to exist. And you see some quotes by famous people, and there's some text. Okay, then what? Then, very quickly, there's problems. Okay? There's not a lot of text with the problems at the end. The problems come in the middle. Okay? And you see more problems, activities, investigations, things for students to do. This is a guidebook, okay? More questions, okay? This topic right here, we don't have time to kind of go through the whole thing. What we've done instead is we would like to kind of show you the net outcome of this, what's happened, and see if you can think a little bit about how you would recreate this.
Okay, so on your table you will see a white envelope. Inside that envelope are a copy of a poem called Looking at Square Root of -1 by Shane Murray. This was a final reflection assignment in one of our classes. The students were asked to write a course reflection. This could be anything in any form they wanted, an essay, a song, whatever. Shane decided to do it with a poem. He was a sophomore criminal justice major when he did this spring of 2013. If there are not, if you don't have an envelope on your table, we didn't quite have enough, see if there's some extra copies on tables near you. We will try to get them around to you if you need them. Okay? And what we'd like you to do is just take a few minutes to actually sit and read this poem. Maybe share, 2 of you reading it? Okay.
And while you're reading this poem, what we'd really like you to do is think about the specific mathematical topics that are included in this poem. This was a final reflection piece. It's great as a poem. What is the mathematics that's involved? Okay? And as you see that, think of questions. What could you do to get general education students to think about this kind of mathematics? Okay? And we'll spend, when you're done with the poem, we'll spend 3 or 4 minutes talking about these questions. To look through the poem. If you want, start circling the specific mathematical topics. Be kind of an educational anthropologist. What was learned in this class? What is the mathematics to which this student refers? And how in the world did general education students get thinking about these problems? What could we build as an IBL experience to get them to do this?
Somebody want to go get some Zooty donuts. Only the president, Winnie House.
Okay. It's not typical in an IBL classroom to give out the answer. But since we're almost out of time, I got to give the answer out a little bit on this one, because this seemed like it was a little bit harder. These are students who are terrified of mathematics, who have bad experiences, who've been disfranchised from the whole thing. Guess what? Algebra is one of the worst things for them. Okay? They are terrified by it. They're not good at it. It disrupts everything. So what do? I am a complex analyst. I couldn't do this project and not have a chapter about the imaginary unit. So what do? You have to find some way in. What is my way in? My way in is to think about complex numbers geometrically. Just switch the script. Don't think about it algebraically anymore. Yeah, of course they have to do some complex multiplication and some FOIL, but you don't call it that because there's numbers, not letters. But you can give them rulers and protractors and they can start measuring angles and magnitudes, and they find patterns in the answers. And they build conjectures. And all of a sudden, oh my God, we don't have to multiply anymore, because if we know the magnitudes and the arguments, we can do the entire thing geometrically. And then what happens? We start taking powers of complex numbers and we find spirals. Wow, that's deep. Somebody gives us an equation like z to the n plus or minus a to the n equals 0. We can solve that entire thing geometrically. Wow. That's cool. That's deep, right? They're doing significant mathematics. Of course, you don't write it in polar form, right? But it's just a representation. They can give it their own language, and they can do amazing mathematical things based on the geometry of the complex numbers. They can understand that it's closed, that the complex numbers are closed under linear and quadratic functions. Okay? They can understand why these things happen. And here's the big one. Why is a negative times a negative a positive? I haven't got the video of that day yet, but that's going to be the best video of the whole 200 hours, because here is a whole bunch of people for which mathematics doesn't make sense, and this is the day that all of a sudden they understand why a negative times a negative is a positive, and it is amazing. And I don't do anything, I just stand back, and all of a sudden this group goes, ooh, hey, wow, boom, all over the class. It's awesome. Okay? Disempowered, disenfranchised students who don't want to be there doing deep mathematics on their own, leaving this class feeling different, feeling empowered finally by mathematics in their last experience. That's awesome.
So now what we'd like you to do is just very briefly show you some other amazing things that students have done and with some significant mathematics. So this is string art from our calculus book, where they actually use tangent lines and derivatives to understand things. They create this string art. This is Nestor, the Nestor curve. Nestor is the mascot for Westfield State. Here are some students from using our dance book, making a maypole from a dance, and then of course studying and learning about the underlying mathematics of the patterns. Here's a student who made a slice form of her face. Okay, and by putting it together is essentially mimicking what is done with 3D printers. And then lastly, here are some students doing some anamorphic art, which of course helps them understand perspective. This is also from our geometry book. So these are some of the amazing projects that our students do, amazing work that they do.
To close, we would just like to close with one other example of a student's final reflection. This is a music major who is also a sophomore in our class, and for his last final reflective piece, he decided to write and record a song, which he sent me as an MP3, which we will now play. This is just part of the lyrics. You'll get a sense of the power of this song from those lyrics.
This is my lament that I must regret these past 7 years. All this time it's on something that I thought I knew, something somebody made me go through. These problems in the way that we grow, we swindle out of something. Some people say math, that just has to go. Why should I bother? Gotta let go. Things we used to know. Gotta find the truth behind the ins and outs. told you, we gotta let go and say math's very slow.
That's it. Thank you very much.
Was a time when I was content and followed to the letter what the man said. Deaf, dumb, and blind.
I'm curious, how long was the time between you announced that problem to the class and they came up with those solutions? So what time frame are we talking about?
The 3A plus 5B problem? Yeah. The 3A plus 5B problem took 2 50-minute classes of kind of dedicated work, and then much smaller periods of sharing out, and then time for students to kind of submit their work. So 2 50-minute classes, and then maybe 20 minutes in another class, and then questions, students asking brief questions at the beginning of class, the next class, while they were waiting, while they were about the assignments that they were writing up, and then they handed it in the next class.
But I'm aware they're thinking the whole time. So what's the time frame from they put the problem all the way to the end?
It's about 90 minutes of class time.
Spread over probably a couple of weeks.
So besides the questions that you ask your students at the beginning regarding what their background is and that kind of what you talked about at the beginning of this talk, what do you do to engage them to set a classroom environment where they feel comfortable sharing, exploring together?
We do a lot of things. With my biographies, I actually have the students share their biographies on the second day of class. And so they get to hear what everybody says. And I do that in a very tried, non-threatening way. So if a student doesn't want to share, they don't have to. But it gives them the environment to share things. I also do a gallery walk the very first day, asking them about how they feel about mathematics, and it gives us an opportunity to start having that conversation right away. And I tell them that there's no right or wrong answer here. I just want an honest answer. And so they'll put up things like boring, ask them, how do you feel about mathematics? Boring, horrible, migraine, all these horrible negative feelings. And then we'll talk about the fact that all the answers are negative. And that's how you set the environment that gives them the space to be able to do that and bring their fears out in the open instead of having to hide it, because of course you don't want to let your professor know that you hate math. But now it's out in the open and we can deal with it.
I would also just add to that look, mathematics has beauty and interest in its own right, and the fact that these students have gotten through 12 years of school having seen none of that, one of our major jobs in general education courses is to get them to see that, and the way to see that is to give them the mathematics to actually involve them in the mathematical experience. So the 3A plus 5B problem is a nice problem for the beginning of the semester because they don't feel any of the angst that they had from something else, and once students get 15 or 20 minutes of that, their whole attitude changes because they're empowered. They feel like they can do it. They're not listening to someone else. There's no stress. They're solving a problem. They're communicating. They're talking about it. They're doing mathematics. And very quickly, within the first 3 or 4 classes, I have to tell students when it's time to go. They are head down, working, arguing, creating, doing things, no idea that it's time to go.
I have 2 questions. The first one is, how do you assess students' work? I find myself having a hard time determining a number when they do all this fantastic work and trying to discriminate the quality across work. And the second question is, how do you handle group work, like when they need to work in groups, and sometimes you have people who just sit back and don't do things, or if you assign them to work outside, they don't come with the homework done. So how do you handle those things?
Assessment is very complicated, and even among the 4 of us, we do things quite differently. The solutions that you saw put up there were solutions that were done as groups, okay? I typically have assignments during the semester where students do things in groups, but I also have the majority of their work is work that's done individually that they write up and they hand in, and then I grade it. And the grading for this class is an enormous amount of work because it's not just looking to see if they got the right answer or the right formula, and so it is a lot of work. Class participation counts. It is difficult to have students work in groups. We often switch groups up. If there are groups where there are several groups where there are students who just kind of aren't pulling their weight, they get put together. Sometimes that helps them.
With our website, we have a blog. We actually just very recently did a whole bunch of blogs on assessment. So if you go to our website, artofmathematics.org, there's in the blog section you can find it. Whole way of that we assess things, and again, with different things with different students. And definitely, I switch the groups every class just about, and that really does help keep the students on pace because they don't want to go into a group and find that everybody else is like 30 questions ahead of them because they didn't bother to do the work. So that actually does work very well.
I have another question on that same topic. What about the other side for the student in the group that takes over and pretty much leads and does all of the work? What do you do to make it so that it's shared amongst all the group members?
Tell the student to stop. We have these
you do. That's
we have these wonderful rooms that have 9 tables in them, but they also have wraparound blackboards on 3 of the 4 walls. And so a lot of times we have the students get up and do their work on boards, and now that they have cell phones, they can record, they can take pictures of their work, which is great. But it's nice to get them up because it's a different energy and everything. And I'll just go around and I will take chalk away from people. She's been writing everything down here. Chalk is yours, you be quiet.
And one of the other things that we sometimes notice happening, though, is the students actually modeling what we do. And you'll actually find that sometimes the stronger students will turn around and will respond to a question from a weaker student by asking a question and not telling. It's an amazing thing to see that happen.
And one other thing that we do sometimes is if there are a few students who have kind of gotten farther ahead as from the class as a whole, we sometimes send them over to listen to other groups. Just pick them up and say, well, that group over there has a really interesting strategy, right, which is completely different from yours. Why don't you go over there and see if you can help them? And the ironic thing is that that person who's been transplanted in the other group has no idea what's going on, because that's not their strategy anymore. And that other group doesn't want to hear about their strategy. They got their strategy that they're invested in, so then this student is, oh my God, how does this work? And is learning something completely new. Okay.
If we have further questions, perhaps you could find the speakers afterwards. It's time for us to move on. Please join me in thanking Phil and Julian.